This lesson marks a real changing point in our study of Algebra 1. Up until this point, virtually everything that we've studied has been related to lines and what we call linear functions. Now, I know we haven't really tossed out the word function at this point, but we've done a lot of solving linear equations, graphing linear equations, linear inequalities, systems of linear equations, and so forth. Beginning in Unit 8, we're going to look at exponents, and we're going to start to broaden our understanding of the different kinds of relationships that we might have. So this lesson here is going to cover some really key vocabulary, and vocabulary is so important because this is how we communicate effectively in mathematics. So we're going to cover some key vocab, and then I'm going to go through 3 properties of exponents, what we call the multiplication properties of exponents. And I don't want to just give you those properties. I want you to have an opportunity to see where those properties come from. So first, let's talk about what an exponent is. We've talked a little bit about exponents earlier in our study of Algebra 2, but we want to get into some of the vocabulary with that. So I'm going to use this is representing an unknown number, and I am going to, just to start out with, use like an exponent of 7, okay? And what the exponent tells us is it tells us how many times a is used as a, and so a to the 7th means a times a times a times a times a times a times a. And this is all multiplication in here, and so we would have 7 a's. Now, when you're writing your exponent, do make sure that you're writing it smaller than whatever number or variable you're making the exponent on, and that it is like high. Okay, it's what we call a superscript. So just to get some of the vocab down. This value here, the a, this is called the base of the exponent. The 7 is, of course, the actual exponent. And when you are multiplying it all out, these are called the factors. Okay, and so when we define what an exponent is, we define it as the number of times the base is used as a factor. Now, when we get into some of the other exponent rules, you're going to notice that that definition starts to fall, it doesn't fall apart because it's still the definition of what an exponent is, but we're going to get into some exponents that look really different, and when you try to apply that definition to them, it's going to seem really weird, okay? So just kind of heads up, we're not going to look at it in this lesson. So we have the base, the exponent, and then the exponent tells us how many times the base is used as a factor. And so you would often see maybe like this generic a to the nth power, okay? And sometimes you'll see that like this, and then there'll be this ellipsis in here indicating that we have an unknown number of a's here, okay? And so we have n factors. So a to the nth power means that you would have to have n a values there being used as factors. And in this case, we don't know what n is, and so we have that ellipsis in the middle there. So we're going to look at a couple of properties of exponents. So for example, if you had, and we'll use usually when I do this in class, I will do like x or something. I've been known to use a's though. If you have a to the 2nd power times a to the 3rd power. Okay, so let's think about what that means. So a to the 2nd power literally means a times a. And a to the 3rd power literally by definition means a times a times a times a times a. Okay, so all we're doing there is we're applying the definition. The exponent tells us how many times the base is used as a factor. Now, what's happening in between these, the a squared and the a to the 3rd? Well, that is multiplication. And so essentially what we have here is we have a times a times a times a times a, or better known as a times a times a times a times a, okay? Which would just simply be a to the 5th power. And what you might note is that the 5 is equal to 2 plus 3, okay? And so you might think, can we just add the exponents together, would that work as a shortcut? So we're not going to go through what's called a formal proof of this, but we will do another example. So let's see, whoops, my hand bumps the change page thing going on there. So let's say we had a to the fourth times a to the, I don't know, fifth. Okay, so what would that be? That would be a times a times a times a. Sorry, my A's are looking a little bit like nines there. A times a times a times a times a. And that's being multiplied. And you can see that we have 4 A's and then we have 5 more, and they're all being multiplied together, which means I have 1, 2, 3, 4, 5, 6, 7, 8, 9 A's, which is a to the ninth. And so it seems, wait a minute, that's not what I wanted to write. Just kidding. Hang on. A to the fourth times a to the fifth, that we can just add the exponents together. Okay, now if we want to, we could try one more example. Here we'll do a to the first power. Now normally we don't write to the first power, okay, because that's just a, and we'll do a to the third. So this would just be a, that's all that ever was, a times a times a, being multiplied together, and that is a to the fourth. And that leads us to our first multiplication property. Okay, so property 1. I don't think it has, I mean, it probably does have, oh, the product of powers property. Okay, so the product of powers property is what we call it. Product means multiplying. What are you multiplying? You're multiplying some things with powers. And here's what it looks like. If you have a to some power times a to some other power, the shortcut for that is to simply add the exponents together. So as long as that's all anybody's doing, they're just adding the exponents together, usually students don't have too much trouble with that. It's when you start mixing the properties together that it becomes a little bit of an issue. But I tell my students all the time, when in doubt, expand it out. So if you're blanking out, you're not sure what you're supposed to do with the exponents, as long as you remember the definition of an exponent, you can expand things out into that factorization and be able to get the property. Okay, next one. Let's do an example like this. Okay, so a to the second power raised to the third power. So we need to make sure we're looking at it the right way. So what I'm going to do is go over the parentheses in a different color so you can see it a little bit better. And we have a squared, and a squared is being raised to the third power. So what does that mean? Well, remember the exponent tells you how many times something is being used as a factor. In this case, what's being used as a factor? A squared. So what this means is a squared is being used as a factor 3 times. And essentially what that does is it brings it back to this property here. Okay, so you've got a squared all to the third power, and then you can, if you want to, you can go and expand each of these out. So remember, when in doubt, expand it out. Each of those a squareds is equal to a times a. What's happening in between them? Well, multiplication. And so essentially, how many a's do we have being multiplied here? 1, 2, 3, 4, 5, 6. Okay, now a faster way to get that would have been to do this. You could have done a to the 2 plus 2 plus 2, okay, because that's a property we've already established that if you're multiplying like bases, that means the base is the same, then you can add the exponents. And you might notice, it looks like there was a little quicker way to do that. What if we did 2 times 3? Would that get us to where we wanted to go faster? So maybe. Let's do another example and see how it plays out. So suppose we have a to the fourth raised to the second power. So remember, the exponent tells us how many times something is used as a factor. So what we're seeing here is a to the fourth being raised to the second power. That means a to the fourth is being used as a factor twice. Now you got 2 ways you can process this. You can go back to this property, which says that if you're multiplying like bases, you can add the exponents. So we could just say a to the 4 plus 4 or a to the 8th. Or if you need to, you could continue to expand it out. Okay. And really, it's important that you're understanding the laws and where they come from and that they're reasonable. Otherwise, you will forget them. I can almost guarantee you, if you don't know where these come from or why they make sense or how to reason your way through them, you'll learn them for like one lesson and then forget them by the time you have to take a test. So, which is not particularly helpful. So we have 1, 2, 3, 4, 5, 6, 7, 8 A's being used there. Okay, and once again, you might say, oh, we could have done 4 times 2. That could have gotten us an 8. Now, maybe you're thinking, but what if it's unique to using a 2? Like, so let's do one more. Let's do a to the 4th power raised to the 3rd power. Okay, so this would be a to the 4th times a to the 4th times a to the 4th, which would be a to the 4 plus 4 plus 4, or a to the 12th. And that brings us to our second property. And you could keep doing these over and over and over again until you personally are convinced. So this is called the power of a power property. And what we mean by that is you're taking something raised to a power and then raising that to a power. So that's why it's called power of a power. It's probably not super important that you know the names of the properties here. I don't require my students to go back and name which property they're using, but some teachers might. And so if you're watching this video and you have somebody else for a math teacher, you want to be paying attention in class and know what your teacher is going to require you to do. I don't require my students to name the properties. I just require them to know how to use them. So property here says that if you raise the power to a power, you multiply the exponents. So where it starts to go kind of crazy for students is like, as long as they're looking at all problems where they're adding exponents, they're like, I got this. And if it's all problems where they're multiplying exponents, they're like, I got this. And then you mix them all up. We have one more property to cover, and this is called the power of a product property. And so we'll explore this. Suppose you have two things. You have A and B. Okay, and let's say in this case, that's supposed to be a 3. It's a terrible 3. It's raised to the 3rd power. Okay, and so I said it, I'll write it out in a little bit. It's the power of a product. So there's the power. What are you taking the power of? A product right there. So it's the power of a product. So what is that necessarily? So let's go back to the definition of an exponent. Definitions are incredibly powerful. I am probably like a broken record. I know my own students think I'm a broken record with this because I'm always talking about the definitions. If you understand what something is, you can figure out all kinds of stuff without somebody having to re-explain it or even teach it to you. So in this case, the exponent of 3 tells us how many times whatever's in the parentheses is used as a factor. So we've got a times b, and then another a times b, and then another a times b. And I'll just do the multiplication in a different color there. In other words, a times b is used as a factor 1, 2, 3 times. Now, normally we wouldn't do this. I'm only going to do this one time. But if you remember way back, when we started our study of Algebra 1 and we go through all these properties and you wonder, why is this important? Here's where it comes in important. We studied the commutativity of multiplication, which basically means that a times b is the same as b times a. Now, what that allows us to do is it's going to allow us to take like this a and b and switch them, because b times a is the same as a times b. And we can do the same thing with these two. And what we can do is essentially apply the commutative property several times, and we can rearrange this so that it's a times a times a times b times b times b. In other words, the order of the multiplication doesn't matter. If you're going to do a times b times a times b times a times b, you might as well do a times a times a times b times a. The order doesn't matter. And the reason why you're able to go there is because of the commutative property. Well, now when we look at it, you can see these two groups forming. We have a times a times a, which is a to the third, and b times b, which is b to the third. Now, going back to the original problem, what this means is when you see an exponent outside of the parentheses, that exponent is applied to everything inside the parentheses, provided, very huge provided here, provided that these are being multiplied. If it is not multiplication, okay, I'm going to try to say this so clearly. If this is not multiplication, you cannot just apply the exponent to everything. Okay, if it's adding or subtracting, we have to go, the definitions still hold, but it doesn't look like this, because if you have adding or subtracting, you can't just apply the commutative property to it, because you have adding and you have multiplying going on at the same time. Maybe I'll show you that, but let's do another one. Let's say a times b to the fifth. So what does that mean? It means a times b, and then a second a times b, and then a third a times b, and then a fourth a times b, and then a fifth a times b, and all those a times b's are factors. And again, what's really critical to this property is that all of this has to be multiplication all the way across. If it's not all multiplication all the way across, you cannot apply that commutative property to do the rearranging. So that rearrangement is going to group all of the a's together and all of the b's together, giving us a to the fifth, b to the fifth. Now, most of the time, when you do this, you don't bother to regrouping. Okay, so I'm just going to put a little arrow here, and I'm going to say, hey, that is optional. That's something that I'm doing while I'm teaching the concept so that you can see why the conclusion that we're drawing is a reasonable conclusion to draw, but it's not something that people would typically do. Most of the time, people will just go across and say, okay, how many A's do I have there? 1, 2, 3, 4, 5. Good. A to the fifth. 1, 2, 3, 4, 5 B's. Good. B to the fifth. And you don't do any more than that. So here's the final property for this lesson. This is called the power of a product property. And this one says that if you have a times b raised to some power, that is equal to a to the power times b to the power. Please, please, please do not say that you are distributing, okay? I actually just defined this the other day for one of my classes. Distribution is very specifically defined as multiplication over adding or subtracting. This is an exponent over the parentheses. So please, please, please don't say it. I am aware that it looks like you're distributing the exponent, and I totally see why students want to go there. In fact, I can catch myself wanting to go there, but it's not the right word to use, so please don't use it. Now, one last thing. I said it doesn't work if you have adding, okay? It only works for multiplication, and then because division is multiplication by the reciprocal, it'll work for division as well. But here's the deal. If you have adding, okay, then what you have is a plus b as a group times a plus b as a group times a plus b. And I have to put those parentheses in there because of order of operations, because we have to do parentheses before we do exponents, which means we have to do the parentheses before we do the multiplication. And you'll notice that now we have this weird mix of operations. We have adding and we have multiplying both, which means that we cannot just go and switch the order of things, okay? It just means we can't do that. We have to carry out that order of operations. So, all right, I'm going to do a couple of example problems so that you guys can see how these properties are used, and then I'll release you to do some practice problems on your own. Okay, so these are just some pretty basic application problems where you just have to apply one property at a time, which is usually okay for students. So the first one is 5 to the third times 5 to the fourth. And again, you're always like, when I tell my students, when in doubt, expand it out. So you can always fall back on the definitions and going through that process of expanding them out. But ideally, you want to get to the point where you're going to say, okay, this is going to end up being 3 plus 4 on my exponents, or 5 to the 7th, okay? And typically we would just go straight to the 5 to the 7th. You really want this to be automatic. Here we've got x squared times x to the 3rd times x to the 4th, which would be x to the 2 plus 3 plus 4, or x to the 9th. Here we've got the power raised to a power. So that is 2 to the 4 times 3, or 2 to the 12th. Now you might be wondering, like, should I find out what those numbers are? Generally not in problems like this. That's a debatable thing. For this one, now this is what we would normally do. We would not write out the 2 times 4. We would just say that's y to the 8th. So we really want that to be automatic for us. Now here, this one looks a little bit different, but remember, math is really consistent, so there's no reason why this should look different or work differently. But if you aren't sure, you can do this: 2xy times 2xy times 2xy. When in doubt, expand it out. So just engage the definition of what the exponent of 3 is. And now you can probably see, okay, this is going to be 2 times 2 times 2, which is 8, and then x times x times x, which is x to the 3rd, and y times y times y, which is y to the 3rd. Next one. Now, these two are interesting. Basically, it's finding out, hey, does the placement of the negative make a difference? Really important question. Answer is probably yes, but who knows? So again, when in doubt, expand it out. So if you're not sure, apply the definition of exponents. So what this means is that the negative 3a is used as a factor twice. So you're going to have negative 3a times negative 3a. Negative 3 times negative 3 is positive 9. A times a is a squared. Now over here, the negative is not being squared. So the squaring is only going with the 3a. So you have 3a times 3a, and that negative is hanging around for fun just out front. And so we have 3 times 3, which is 9, and it ends up being a negative 9 because you got the negative sitting around out there. Some people will think of it as like negative 3. And then a times a is a squared. So the placement of the negative does matter, whether the negative is inside or outside the parentheses, because that controls whether or not the negative is being squared. And here we have that sneaky little example with the a plus 1. So for this one, we don't really want to mess with that a plus 1, but we can go ahead and do the multiplication on the exponents there. But don't tell me that that is a to the 10th plus 1 to the 10th, okay? That is actually not true, and you'll do a lot of damage if you say that's true. So make sure that you are clear on when you can apply the property. So that's it for this lesson. I'm going to put some practice problems on the next slide, and you can pause the video as always and do them out. Okay, here we go. 4 squared times 4 cubed. 2 is x times x to the 5th. 3 is 3 times 7 all to the 4th. 4 is 2x all to the 3rd. Notice how I am putting the word all in there to indicate what is being raised to the power. Number 5 is negative 5a all squared. 6 is 2x cubed times 3x all squared. 7, 3y squared times 2y cubed. 8 is 2t all cubed times negative t squared. 9 is abc squared all cubed times a squared b all squared. And 10 is negative 3xy squared all to the 3rd times negative 2x squared y all squared. Pause the video, work these out, show as much scratch work as you need, and then unpause to check your answers. All right, here goes. As always, pause the video at any point because I only have 6 minutes to go through 10 problems, so I will probably talk a little fast, so pause it if you need to. First one is simply adding the exponents, so 4 squared times 4 to the 3rd is 4 to the 5th. You are welcome to actually figure out what that number is. That's fine. It's a little debatable. You'll notice that I do it differently in different places. For the second one, what's important to remember is that x to the first power means that x is being used as a factor once, so it's just there there one time. And so you'll notice that I put the 1 in green there just as a reminder that when you add the exponents, you're going to do 1 plus 5 to get 6. For number 3, there's 2 different ways you could take this. One is by applying the exponent to both the 3 and the 7. So you could write this as 3 to the 4th times 7 to the 4th. Or you might look at that and say, well, order of operations says I should do the parentheses first. And do 3 times 7 is 21, and just write 21 to the 4th power. Either one of those, like, you can make an argument unless your teacher tells you have to do it a certain way. So for the 4th one, we have 2x all to the 3rd. And so the fastest way to do that is to say that this exponent applies to everything inside because it's all multiplication. Please remember that. So it's 2 to the 3rd, x to the 3rd. 2 to the 3rd is 2 times 2 times 2, which is 8. Sometimes students will say, well, can I leave it as 2 to the 3rd? Follow your teacher's directions. Usually if the number is small enough, you will be expected, or be advantageous to expand it out and get the actual number. If it's not, like 21 to the 4th is some huge number, you'd leave it as an exponent. And this step in here is an optional step. Okay, if it helps you to see 2x times 2x some 2x, go ahead and write it. There's nothing wrong with it. If you don't need to write it, totally fine. Next one, negative 5a squared. So this one with the negative, a lot of students are going to be more comfortable writing it out just so they can see it. So it's negative 5a times negative 5a, which is going to be positive 25a squared, because you'll have a negative times a negative. For the next one here, I actually did do the expansion out because now, beginning in number 6, we're applying more than one property at a time. And so there's more steps involved. So the first thing I did was I took the squaring and expanded it out. Then I did a regrouping step. I don't always do that. 2 times 3 times 3, x to the 3rd times x. So this ends up being 18, and this ends up being x to the 5th. For the next one, all I did here was I removed the parentheses. 3 times 2 is 6, and then y squared times y to the 3rd is y to the 5th. Make sure you know when you're multiplying and where you're adding there. Next one. The last 3 I actually did 2 different ways. So this is the way that I would do it. I would do 2 times the, well, what I did here was I applied the 3 to everything inside, to all the factors inside. So I have 2 to the 3rd, t to the 3rd. Then I just removed the parentheses and opted for a different multiplication symbol. 2 to the 3rd is 8 times the negative 1, which is right there, which gives me the negative 8, and then t to the 3rd times t squared is t to the 5th. This way over on the left shows more of that expansion. So 2t times 2t times 2t times negative t times t. Remember that the negative is not being squared. It would be squared if the 2 was on the outside, but the 2 isn't on the outside, it's on the inside. So the negative is only sitting there once. I would almost put money on if you did something wrong, that's probably what it was. Okay, so make that correction if you need to. 2 times 2 times 2 times the negative 1. Again, we have that negative 1 there. And then what I did was I grouped all the t's together, and there were 1, 2, 3, 4, 5 t's. So you have negative 8 t to the 5th. Okay, and there's a lot of flexibility in like what work you might show for that. Number 9, I did the same thing. So I kind of worked it out 2 different ways for clarity, and you can pause the video, of course, and kind of study the different ways. But the first way I did it was I applied the 3 to everything inside. So this is a to the 3rd, b to the 3rd. But remember, when you have a power raised to a power, you're going to multiply those exponents, which is where the 6 came from. Over here, same thing. A squared raised to the 2nd power is going to be 2 times 2, which gives you 4, and then b squared. If you look at your a's, a to the 3rd times a to the 4th is a to the 7th. B to the 3rd times b squared is b to the 5th. And of course, the c to the 6th just comes down. And so that's how I would do it. Probably wouldn't try to skip this step though, even though I think I could. I don't think I would. Over here is the expansion out. Okay, so I actually took the exponent of 3 there and expanded it out, and the exponent of 2. And then what I did was I underlined like all the a's in red, so you can count 1, 2, 3, 4, 5, 6, 7 a's, 1, 2, 3, 4, 5 b's, and 1, 2, 3, 4, 5, 6 c's. Last one. Again, this is how I would do it. I'm totally going to run out of time on this. I would apply the 3 to everything. So negative 3 to the third, x to the third, y to the sixth, and then negative 2 squared, x to the fourth, y squared. Negative 3 to the third is negative 27. Negative 2 squared is 4. Everything else is the same. And then negative 27 times 4 is negative 108. That was my scratch work right there. And then there are 7 x's and 8 y's. X to the third times x to the fourth and y to the sixth times y squared. This up here is that big long expansion which allows you to see more, and we arrive at the same answer. So I'm out of time.